Okay, and we're live as of now. So I've got Niall and Kyle with me for Calc 2, looking at some homework questions instead of what was planned. So this will be a little bit off the cuff, and we'll see how we do. I don't have any of these prepped, so we'll just do them together blind, and then we'll check our answers afterwards, I think. Also, don't have touch input working at the moment, and I think I would need to restart the computer in order to get that working, so we're just going to go without it. Alright, so for this first one, we've got a function f that is continuous and decreasing with values shown here in the table. I want to use the trapezoidal method first to estimate area between f and the x-axis on our interval. So let me see what we know first. So Niall, starting with you. What's our trapezoidal Riemann sum? If I wanted to set this up, what would our first trapezoid be? Okay, if you're talking, you're still muted.
So we have to use like 1/2 times base times height 1 plus height 2.
Okay, so do this. Make a table. How many spaces do I need? I need that. 8. Okay, so you told me the trapezoidal Riemann sum is going to look something like this. And you said 1/2 of our heights. That's just getting our average height times the base. And I'm going to keep doing that for each rectangle that we have here. So that means this will be the sum instead. Okay, so for our first trapezoid here, what will that end up giving us? If I average these two heights together and then get the space between them for the base. Niall, still with you? What's our first height, second height, and the base?
7.6 plus 5.7.
Okay, 7.6 plus 7 times. Go for
The
it.
base is gonna be 1 point. No, not 1. 0.8, right? No, 7.
Okay, 0.7 was the difference between 3.2 and 2.5. So what we've really done is we've created our first trapezoid. Our first trapezoid that would look like this between 2.5 and 3.2. Okay, we're going to keep doing that, creating more and more trapezoidal shapes between all of these spaces. Okay, so let's finish this one off then. So this will be all of this. Okay, Kyle, what's my next one? I'm going to factor out this 1/2, I think. Kyle, are you there?
Yes.
Okay, so we've got our first trapezoid. For my second trapezoid, what are my two heights?
5.7, 4.2.
5.7, 4.2, and our base?
Base of 8.
Base of not 8.
Wait. Oh, 0.3.
0.3, okay. Um, okay, what's happening here? Oh, I know what's happening here. There we go. Okay, so I'm just going to keep doing this for the rest of our trapezoids. I think I'm going to run out of space, so I'm going to erase this part, and we'll keep going from here. Niall for the next one.
So we have 4.2 plus 3.8 multiplied by that. So, no, never mind. Multiplied by the 0.5.
0.5. Okay, can you do the next one too? So
Yeah. 3.8 plus 2.2 times 0.6.
0.6. Okay, and Kyle, last one. Oh. Okay, so this will be 2.2.
Plus 1.6 times 0.4.
Alright. Then I'm going to multiply all of that by 1/2. So I'm going to type this in our calculator. And we'll see what we've got. So I've got 0.5 times all of this. 7.6 plus 5.7. Times 0.7. Okay, 5.7 plus 4.2 times 0.3 plus 4.2 plus 3.8 times 0.5 plus 3.8 plus 2.2 times 0.6 plus 2.2 plus 1.6 times 0.4. Okay, and then I should close that last parentheses for that 1/2, and that should give us our trapezoidal Riemann sum. So I've got 10.7 total after all of this. From 2.5 to 5. Any questions on part A? Okay, so for part B, I'm going to find our average rate of change of f on the interval from 2.5 to 5. If I'm looking for our average rate of change, then Kyle, what do I need to do?
We must derive. Wait, average rate, so 1 over b minus a times a to b.
Okay,
But we don't.
that would be an average value, and we don't have a function, so we can't do that. So what is a rate of change?
The velocity, the speed velocity.
Okay, we don't have any units here, but another word for rate of change would be a slope. So I'm really looking for an average slope.
So should we derive?
We don't have a derivative, so plus a derivative is an instantaneous slope, not an average slope. Derivative is a slope at 1 point. Average slope would be a slope between 2 points. So how do I find the slope between...
Delta y.
Yes.
Delta y over delta x.
Delta y over delta x. Okay, so our change in y over change in x. What's our change in y for these values?
So is that the difference between 2.5 and 2.5 and 5?
That's our change
So-
in the x values. So I can put that in the bottom though. So 5 minus 2.5 is our change in x.
That means the change in y will be f of x. So 7.6 minus.
Okay, it would be, but we're going to
minus
start at
1.
the end. So this will be 1.6 minus 7.6.
1.6 minus 7.6. So that would be like negative 6.
I'll write this out one more time. This is f of 5 minus f of 2.5 that we just did over 5 minus 2.5. Okay, so you said this is on top negative...
Yeah.
Okay, you said negative 6. On bottom I would get 2.5. So this is negative 6 over 2.5. I'm going to multiply both the top and bottom by 2, so I can get rid of that 0.5, and this will become negative 12 over 5, which is as much as I can reduce, I believe. I'm going to move this negative to the top just so I don't accidentally think that's part of the fraction sign later when we zoom out. Any questions on our average rate of change? Okay, so then over to C. If I want the instantaneous rate of change for f at x equals 2.5, I'm going to stick with Kyle for this one. This has been kind of a recurring issue for the last week or so. So if I want the instantaneous rate of change of f at 2.5, then what are we actually looking for? Ideally.
Instantaneous rate of change. So could the average between not average the average between 2.5.
Okay, so an instantaneous rate would not be an average, it would be a derivative at a point. But because we're making an estimate, we can use an average for the estimate. Instantaneous rate of change is another way of saying instantaneous slope, which is the same thing as a derivative, slope at a point. I want to estimate the derivative when x is 2.5. Okay, because we don't have an actual value for the function, to estimate the derivative, we can use an average slope. But what 2 points would you want to use for the average?
2.5 and hopefully 2.3.2.
Yep, so we're just going to use the closest points. function. Okay, so going off of what you told me, we need to get the average slope between 2.5 and 3.2. So what should we write?
So we could use a slope and not slope and FB. We could use the one we used recently, FB minus
Perfect. I'm going to use the exact
FA.
same one that we just did. So average rate of change. But this time going from f of what value?
F of 3.2 minus F of 2.5.
Perfect. Over f of 3.2 minus f of 2.5 divided by
5.7 minus 7.6.
Okay, divided by 3.2 minus 2.5, and then we'll go in and we'll plug in for those f's. So when we go to substitute for f of 3.2, that would be 5.7. And when we plug in for 2.5, that'll be 7.6. Okay, so this will be over 3.2 minus 2.5 is 0.7. What is 5.7 minus 7.6? Okay, I'm going to zoom in here. So here's what we got so far.
Like negative 1.9, negative 1.9.
Okay, negative 1.9 over 0.7. I think in order to simplify this, I'm just going to multiply both sides by 10 to get rid of our decimals. So that'll give us negative 19 over 7. And then we don't have any units, so I can leave it just like that. Okay. So one more time. I'm kind of picking on you a little bit. That's only because I feel like we've had trouble with this the last 2 or 3 times that I've called on you for average rate of change. If we've got an average rate of change, we're looking for an average slope. A derivative is an instantaneous rate of change, or the slope at a point, or the slope of a tangent line. Anytime that we are looking for an instantaneous rate of change, we would normally derive the function. If we need to estimate the instantaneous rate of change, then we could use an average. If we were asking whether the rate of change was increasing or decreasing, now you're talking about the rate of the rate, and we would be looking at the second derivative. So if the rate of change is increasing, then our function would be concave up. If the rate of change is decreasing, then our function would be concave down. Any questions on vocabulary stuff? You have no trouble with these when you understand the question. I feel like this is just a recurring vocabulary thing. Okay, cool. So for part D, g of x is the inverse of f. I want to estimate the slope of the inverse function when x is 4. Niall, over to you. Do you remember what the derivative of an inverse function is?
Oh, yeah. 1 over f prime. And inside, it's going to be f inverse.
Okay, so you said the derivative of an inverse function. Okay, so in this case, g is the inverse of f, so g prime is going to be 1 over, say one more time.
1 over f prime, and inside it's going to be inverse f. Okay.
Okay, cool. So we're going to use that formula. Now the inverse function is what happens when we swap our input and output. So in this case, if our input for g is 4, then what is the output?
Wait, just take it.
Yep. An inverse function is what happens when we swap the input and output of a function. So if the input of g is 4, then what is the output for g? What is g at 4?
Not sure.
Okay, Kyle, any ideas?
Estimate the slope. Do we find the average again? Between 4 and SNES neighbor numbers.
We're pretty close, so let me do this maybe. So, okay, once again, an inverse function is what happens if we swap our inputs and outputs. So that means if the output of f is this line, then that should be the inverse for g. So this is like this. Okay, so right now this is x and f of x. If we're talking about g, these would flip, right? Okay, so when our x value is 4, then my g of x would be the opposite of my y value. So that would be g of x is going to be 4 at that point when x is 3.8. So we can get an estimate by looking at the points around it. I know when x is 4.2, g of x is 3.5. And when x is 3.8, g of x is 4. So I could get an average slope from that since we don't have an equation for the derivative. Okay, Niall, I'm going to jump back to you. Okay, we don't have an equation for f, but we can estimate using an average slope, which I think was what Kyle was suggesting. So Niall, over to you. Taking a look at this, our g of x is what's on top, our x values are what's on bottom. If we want to get our average slope of g at 4, so we want to estimate g at 4, then how would you set up our average slope?
The average slope is always fb minus fa over b minus a. And in this case, like, g of n can be acting as f of b, not f of b and f of a.
Okay, yes, but help me set it up. So which one's going to be your y2 and which one's going to be your y1? So this first one will be what?
4.0 minus 3.5 over 4.2 minus, no, that's 3.8 minus 1.2.
Okay, that would work. Normally I would increase my x values, so we would flip that, but as long as you keep it the same for the top as you did for the bottom, for which point you did from which point, then we should be okay. So I'm going to type out what you just said, but that's correct. So this is going to be average slope of g of x from x equals 3.8 to x equals 4.2 is roughly g prime at 4, which equals this. G at 4.2 minus g at 3.8 over 4.2 minus 3.8. G at 4.2 was 3.5, g at 3.8 was 4. Okay, let's zoom in so you guys can see. Okay, so this is going to give me 0.5 negative over 0.4. I'm going to multiply through by 10 to give us negative 5/4. Okay, just ran out of space there. Quite enough. There we go. Okay, any questions on part 1? Okay, I've got Kindle loading on the other screen so we can check. Oh wait, that's AB. Never mind. C2 backwards. Oh, CAB solution 567. Okay, here we go. So 10.7. Okay, 10.7, negative 2.4. That is negative 12 over 5, so we're okay. Negative 2.714. That's 5.7 minus 7.6 over 0.7. Okay, that's fine. And then okay, so they're saying interchange x and y. Okay, we did that. Okay, they've got different answers for the estimate though. What did they do? They did g of x would have been 3.5. 4. Did I copy numbers wrong? Three 3.5 and 4 should be on top. That's fine. We did that. From 3.8 to 4.2. 4.2, 3.5 at 4.2. 4 at 3.8, 4 at 3.8. Okay. Negative 1.25. We do match. Just not paying attention. Okay, so negative 1.25 is negative 5/4. So that would have worked. Okay, we didn't solve it exactly the same way that they did, but we did get the same answer they did, so we're okay. Any questions on what we did? Alright, Niall, what was the other one you chose? Which number?
5.
Number 5, okay. It's all 4, 5. Okay. I guess we'll do this in 2 parts since this is already split. So for the first part, we have a bungee jumper that reaches a point in their jump where the cord is 100 feet long with a 1/2 inch radius and stretching. She's still 80 feet above the ground and falling at 40 feet per second. You observe her jump from a spot on the ground 60 feet from the potential point of impact as shown in the diagram. Oh, I'm looking at the wrong one, aren't I? Okay, as shown in the diagram above. Let's get rid of this for now. We'll reopen that. Okay, so as shown in this diagram here. Assume the cord to be a cylinder with volume remaining constant as the cord stretches. At what rate is the radius changing when the radius is 1/2 a foot? Okay, Niall, starting with you. What is the volume of a cylinder?
The volume of cylinder radius square height times.
Okay, I heard pi r squared times
height.
height. Okay. So we were told that our volume remains constant, the amount of space within the rope remains constant, but the rope is stretching as she jumps. So if that's true, then her radius is changing and her height is changing. So I can derive this, and we'll figure out what her radius is changing at. I'm going to write in a different color. Let's do red. Okay. So if we derive this, and our volume is constant, then what is the derivative of our volume right now?
So we find it to be 2 pi r times r prime times s.
2 pi r times dr over dt, okay, times
Height.
height, plus
Wait, we have plus?
product rule.
That's what. Pi r squared dh over dt.
Okay, and then one more thing before you mute. If I derive v, what happens to the left side?
Becomes 0.
Becomes 0, perfect, because we are our volume remains constant, so the change in volume over change in time is 0. Okay, over to Kyle next. I'm going to plug in values that we know and solve for what we don't know. So taking a look at our question, what is the radius of the rope right now?
1/2.
Okay, the radius is 1/2 of a foot, so I'm going to type in 1/2 everywhere that I see a radius. dr over dt is what we don't know, so I'm going to leave that. What's the height right now?
The height is 60 feet from the potential. Wait, she is still 80 feet above. Around this one. 80 feet? Wait, where's the... Is this the chord? Oh, okay, 100.
100. Okay, good call. So this is the height of the cylinder, and the cylinder is the chord, not her height above the ground. So this h for our formula is actually 100, or the height of the cylinder. Okay, so that's pi times our radius squared times dh over dt. How fast is she changing in her height? How fast is the cylinder's height changing?
40 feet per second.
40 feet per
That's all.
second. Perfect. Okay. So that's everything we need in order to solve for dr over dt. So we just need to solve for dr over dt now. So let's stick with Kyle and we'll solve for that last variable.
So we subtract pi 1/2 squared 40 from both sides.
Okay, what's 1/2 times 1/2?
Pi squared.
Sorry. 1/2
Sorry?
times 1/2?
Oh. I was like, I thought pi. Sorry. 1/4.
1/4. Okay, so I've got pi over 4 times 40. We can simplify again. And then let's simplify what we can from this one too. So I've got a 2 and a 1/2 that can cancel. So I'm left with what's left in this term?
2 pi. Just pi 100. Pi times 100.
Okay, 100 pi times
dr over dt.
dr over dt. What's 1/4 of 40?
10.
Okay, so this is going to be negative 10 pi on this side. Alright, what else can we do in order to simplify?
Good. Derive. It's not derive. Divide. Divide 100 by both sides.
Okay, I do that all the time too. So I'm going to divide negative 10 pi over 100 pi. So this will be negative what?
Negative 1 over 10 pi.
Oh, negative 1 over 10.
Oh, and just negative 1 over 10.
Just negative 1 over 10 is dr over dt. What are my units?
Inches. Since it's inches per feet? No, inches per second.
Wait a minute. I didn't actually notice this. We've got different units, don't we, for our measurements? We said the chord is 100 feet long, but the radius is actually measured in inches, not feet. Okay, so I do need to convert some stuff. That's going to change our radius here. So I'm going to have to go back up to the point where we actually plug numbers in. So this shouldn't just be 1/2 if we're measuring in feet. Okay, you guys won't know this likely, so we're not in the US, so we don't use English units. But there are 12 inches in 1 foot. Okay, so there's 12 inches in 1 foot. I think this will be easier, maybe, to convert our... Well, I actually don't mind. So, do you want to convert everything to be in inches, or do you want to convert everything to be in feet?
Feet.
Okay, we'll leave everything in feet. So that means our radius is 1/2 of an inch. So how many feet is 1/2 of an inch?
1 over 24.
1 over 24, perfect. So I'm going to change both of these 1/2s to 1 over 24. Okay, and we'll do this again. Okay, so you said subtract this term from both sides. So that's going to give me negative 40 pi over 24 times 24 is equal to 200 pi over 24 times dr over dt. Is there anything that I can cancel on both sides?
not 24.
Okay, I can cancel 124 from both sides, you're right. So multiply both sides by 24. What else can I cancel?
Pi.
Can also cancel pi. Alright,
Hmm.
let me do that, I guess. So this is 40 over 24 you've got left on this side, and this is 200 times dr over dt. Okay, anything else that can simplify?
We could divide by like 20.
Okay,
Like
if I divide
10.
by...
2.
Okay, you wanted to divide by 20, so that'll give me negative 2 over 24 equals 10 dr over dt, if I divide by 20 on both sides. What else?
It turned out to like negative 1 over 24, or we could do like divide by 2 to both sides. So negative 1 over 24 is equal to 5 dr over dt.
Okay. So this would be negative 1 over 120 then is equal to dr over dt, right? You said divide by 2 on both sides, then divide by 10 on both sides, right?
Yes.
Okay, cool. So, what are our units right now?
Feet per second.
Feet per second, perfect. Okay, any questions on part A? Okay, looks like we lost Niall. I'm gonna see if I can get him back really quick. Also got a blank notification from Aileen. I have no idea what that means. Maybe send a message and delete it.
Maybe.
It's lost the call. If you click calculus AB and BC combined and request to join, you can rejoin once your connection allows. Alright. Make sure no one else is posting here too. Nope. Okay. So I guess we'll finish this one off. From our observation point, I want to know at what rate is the angle of elevation to the jumper changing when the radius is half an inch. So they've got F and T, but they haven't actually defined F. I think I maybe copied a picture from the next problem. I'm going to double check. I did. Okay, so this graph has nothing to do with the problem. That's why I'm so confused. Sorry about that. Alright, from our observation point, I want to know what is the rate of the, at what rate is the angle of elevation to the jumper changing when the radius is 1/2? So taking a look at our picture, that angle of elevation is our theta. So in this case, if I wanted to set up an equation involving theta, what would our equation be?
The tangent. I was gonna say tangent, the inverse tangent, I think.
Okay, so the
just
tangent
tan-
of theta should be equal to what?
To 80 over 60, so what? Y over x?
Okay, y over x. And in this case, because she's jumping up and down, her x value is not changing, but her y value is. So what that means is I can use this equation to solve for the angle right now. But when we derive this equation, the derivative of x in terms of time will be constant. The derivative of y in terms of time is going to be how fast she's falling, and the derivative of theta in terms of time is really what we're looking for.
Okay.
Alright, so this is a 3, 4, 5 triangle, 60, 80, so this side should be 100. I'm going to leave it like that, I think. 100. And then maybe not actually solve for our angle. And I think this will work out. I'll show you what I'm thinking in my head in a minute. But this is theta is equal to the inverse tangent of 60 over 80 right now, right?
Yes.
Alright, so let's go ahead and derive this now. If I derive our original function, the tangent theta equals y over x, then I'll get a new equation. What's the derivative of the tangent of theta in terms of time?
Sorry, so the derivative tangent? Theta?
Yep.
Oh, secant squared theta.
Secant squared theta. Okay, then chain rule. If I'm deriving in terms of time, I would need to multiply by...
D theta over dt. Is it dt?
Yep, d theta over dt if I'm deriving in terms of time. Okay, and then for the derivative of y over x in terms of time, this will become...
y, just wait.
Normally,
Y prime
okay.
x.
Normally I would use quotient rule for this. I'm going to skip a step though because we know that x is constant, I believe. She's not moving left or right. So because we know that x is constant, then the 1 over x is going to stay the same. So if that's constant and not a variable, then this is just going to stay 60. Okay, what's the derivative of 1 over 60 times y?
Just, it would be 1 over 60 dy over d theta. dy over dt.
dy over dt, perfect. Okay. So this is the secant at the same angle that we had here. So at this angle, the cosine would be adjacent over hypotenuse, which would be 6 over 10 or 3 over 5. So the secant would be the flip of that, which would be 5 over 3. So that means the secant of my angle is 5 over 3, and then I'm squaring that, times d theta over dt is what we don't know, is equal to 1 over 60 times, what is dy over dt? Okay, I'm getting another message, so I'm going to jump over. Do you remember how fast she is falling?
40 feet.
Okay, she was falling, 40 feet per second, you're right. So should that be positive or negative in this case? For the change in y?
Negative.
Negative in this case, because her height is changing at that rate. Double checking to make sure these are measured in feet instead of inches, because we messed that up last time. 60, 80, so 60 feet. Okay, so these are all measured in feet. I can't really tell with the picture, but the question says these are measured in feet, so this is also feet. So right now everything is feet. Okay, and I need to solve for d theta over dt. So to solve for d theta over dt, what do I need to do next?
Divide 5 over 3 squared from both sides.
Okay, so that'll give me
So,
d theta over dt is equal to, I've got negative 40 divided by 60 is the same thing as negative 4 over 6, or negative 2/3. Okay, so I've got negative 2/3. If I divide by 5/3 squared, when I divide by a fraction, I can flip and multiply. So that's the same thing as 3/5 squared. Alright. And then 3/5 squared, what is 3/5 squared?
9 over 25.
9 over 25, so this is really negative 2/3 times 9 over 25. Alright, what can cancel?
Mm-hmm. Can we find like is it greatest common factor?
If we're multiplying, we can just multiply straight across.
Oh, so 2 times 25 and 9 times 3.
This would be 2 times 9 and then 3 times 25. So multiply straight across. Or negative 18 over
75.
75. Okay, and then we can divide that by 3 on both sides. So if we divide by 3 on both sides, this becomes what?
Negative 6 over 25.
Okay, and I believe that's as much as we can simplify. What are our units?
D theta over dt, so that is not radius,
Radian?
degrees per radians.
believe we're not
second?
measuring in... Okay, it didn't say, so I'm going to make this radians, but radians per
Second.
second. Um, okay. Any questions on anything we did?
No.
Okay, I'm gonna load our Kindle again. We'll double check our answers. Niall told me he had a problem with his device and is restarting, so he might jump back in a minute.
Excuse me.
Okay, this is BC4. Nope. BC5. Uh, -1/10 inches per second, but there are 12 inches in 1 foot. So that answer still matches what we have. And then -6/25 radians per second is correct. Okay, so we look good. Okay, any questions on anything from the homework? Anything else from question 1 or 5?
No. Not yet.
Alright. Let me save this one then. For homework. Okay, so what I had planned to do today was to go back over separable differential equations. I'd also promised that at the beginning of the lesson I'd go back and talk about the last question that we did last class period. I did add to the recording at the end on YouTube what the correct answer was for that one. But let me go back and we'll finish that one up. And then maybe we'll have time for one more FRQ after that. Okay, I've just lost the drive. So let me undo this one. Come back. There we go. 3. Okay, none of those are what we did yesterday. Downloads. Hopefully it's the one we wrote on. Okay, yeah. Okay, none of those are what I was thinking of. We had a polar equation we did last time. I thought. Let's see. Do if I go back in history? There we go. Alright, so this was 2019 Q2, and we hit a wall yesterday when we were doing this. For the last one. So my problem was when I went to graph this, I didn't graph cosine theta, I graphed cosine 0, and then we kind of got stuck after that. So I'm going to quickly graph what this looks like in the polar equation one more time. Let's talk about what's happening as our k approaches infinity. So this says there's some portion of this area S, while I'm typing this. That's going to be covered as this k number constant that I'm multiplying by cosine theta approaches infinity. It's 3 root theta sine theta squared. Okay, then from 0 until root pi. Okay, so with this r equals k cosine theta, if our angle is 0, then this is going to be 1 times k. So I'll have infinity, and I'll be way out here on the side, right? And then as k approaches pi over 2, at pi over 2, we'll hit 0. So I'll come down to 0. Something like that. And then after pi halves, we'll bounce on the other side. In order to create our circle. As our number gets bigger and bigger and bigger, this radius is going to get bigger and bigger and bigger. That means this side of the circle is going to get closer and closer and closer to the y-axis. So I'm going to see if I can model that really quick. So I graph this. Here's our two functions. I'm going to zoom in so that we can see what's going on. And then we'll keep our window the same from there. Okay, so my two functions, s and our curve, from 0 until the square root of pi. If I increase this value for k, so we'll go to 10. Then our circle is going to move a little bit closer to the axis. Okay, so here's a really big value. You can see we're getting closer and closer and closer to that axis as I get bigger and bigger and bigger. So if I take the limit as k approaches infinity, then I'm going to enclose a larger and larger portion of this area S as my radius gets bigger and bigger and bigger until eventually I'm going to approach a number that's infinitely close to all of the area of S, which is going to be the area from 0 until pi over 2 of our r function. And if we trace that, then our area of k is going to be 1/2 of the integral from 0 to pi halves of r squared d theta, or 1/2 times math 9. And the integral of variables, y variables function, I've got this stated as y2 right now. Y2 squared in terms of theta. From theta equals 0 to theta is pi over 2. Can't do r squared. R is 3 square root theta sine theta squared. That was good. R2 squared. Open equation, variable, input, output, Lower bound, upper bound, that looks fine. Okay, this out, try again. Open, close, open, close. Oh, R2. I'm looking at the wrong one. Try this again. I'm typing in Y2, but I'm stored in a polar, not a rectangular equation at the moment. Variables, Y variables, polar. R2, not Y2. Okay, there we go. So it was throwing me an error because I didn't have anything stored in Y2, but that gives us 3.32. Any questions on what we did here?
No.
Alright. I've got 15 minutes left. That might be time for an FRQ, but that's not time enough to introduce the topic before it, so I guess we'll do one more FRQ on a topic we've already covered, and then we'll check our answers afterwards, maybe. Let's do this one for disk and shell methods. I think we had some issues there a while ago. Okay, so I will need a graphing calculator for this one, but we've got a region R bounded by the graphs of square root x and x over 3. So I've got a graph that looks something like this. Actually, we'll just graph it in a graphing calculator. In function mode, root x and x over 3. I'm going to change my window. We'll go from x equals -1 to x equals 2. Since I know these intersect at 1 and 0. Actually, they don't. This is over 3, not just x. I'm going to go a little bit beyond that. And my y values need to get up to y equals 2 should be enough to give us a little bit of space. Okay, let's graph. Okay, so here's our two functions. I need to go a little bit further, actually. Okay, here's our two functions and where they cross. If I want to find the area of this region R, what would I have to do?
The y is equal to 1/2. Is it 1/2? Yeah. 1/2 of from. There's no. Can we find the intersection point between in the graph? Or
We can get the intersection point. I'm going to hold that thought for a second. So I'm just looking for the area of R, not a volume. How do I find the area between two curves?
area is equal to. The 1/2. Was there 1/2?
Okay,
Yeah,
there's no-
1/2 from AB.
Okay, 1/2 is going to be, that's polar area, I think.
Oh, okay. It's polar area. So it's just square root of x squared minus x over 3 squared dx.
Okay, so my area between two curves is the integral of top curve minus the integral of the bottom curve. So I'm going to have an integral from a start point at 0 to an end point at whenever the square root of x equals x over 3. So I'll solve that in a second. But we're going to go to that intersect of what's my top function and what's my bottom function.
So this would be square root of x minus x over 3.
Okay, and I'm going to integrate that in terms
dx.
of x, okay? So we are going to intersect whenever the square root of x equals x over 3. Okay, so if I square both sides right now, this is x equals x squared over 3. And then if I subtract x from both sides, I'll get 0 is equal to x squared over 3 minus x. If I factor out an x, I'll end up with this. Okay, so what are the two x values that will make this okay?
0 and 2.
Oh, I didn't square that, sorry. I'm going to square this. This is going to be 9, not 3 on bottom. Okay, so 0 or...
1 over 3. Oh, 1
Uh,
over
what
3
over 9
7.
minus 1 will give us 0?
So 0 plus 1 is 1 divided by 1 over 9. Wait, I don't know what I was thinking. 9?
9. Okay, so if x is 9, this will be 9 over 9 minus 1 is 0, so I'll still get 0. Okay, so I'm going to go to 9. That should give us the total area of R. So I'll type that in a graphing calculator. If we integrate the square root of x minus x over 3, which one's which? Square root of x is right now my y1. Let me close that off so I can use that. This is variables y variables function y1 minus variables y variables function y2 in terms of x from 0 to 9. Okay, so we've got 4.5 for our area. For part B, we want the volume of the solid generated when R is rotated about the vertical line x equals -1. Okay, so we're rotating about a vertical line. I'm going to graph this in the calculator just so we can get a visual, I think. Maybe just draw over it. Let's go to -2. Actually, let's go to -7. Actually, need more space than that. -12. Okay, so what we're going to do is we're going to take this area, and we're going to spin that around a vertical line x equals -1. So that's going to look something like this. Here I've got a vertical line at x equals -1. And I'm going to spin the rest of this around that. Flip horizontal. Okay, so I'm going to end up with something like this. Tools, particular slides. After I spin around. Alright, something like that. So we're just going to spin around this axis in order to create this shape. Am I going to use disk method or shell method?
Disk method.
Okay, we use disk method whenever we're spinning around a horizontal line. In this case, I'm spinning around a vertical line. So we're going to use shell method instead.
Wait.
Okay, so for shell method, zoom in here again. I'm going to pick a random x value somewhere in the middle, so like this. And I'm going to take that x value, and we're going to spin it all the way around our shape, so that I end up with something like this. After we spin it around, we'll end up with a cylindrical shape. This cylinder is going to have a height that is here in red. Of how much?
Oh, d y over d of dy.
Okay, so our infinitely small point is actually going to be this value up here. I'm going to change colors. This part from here to here is going to be my infinitely small dx. Okay, but I am going to have this line here in red. My height is going to be the difference in y2 and y1. Or in our case, those were square root x and x over 3. So something like that. I also have a distance around the top of the circle. So that's this circle that I've marked here in blue. For shell method, that distance is going to be 2 pi r. So that's the circumference, 2 pi r. Okay, any questions on what's going on with our picture?
No questions.
Okay. What's our volume with this method? Or, sorry, with shell method?
There's 2 pi. 2 pi times the bounds. What are the bounds?
Okay, 2 pi times the integral.
The integral.
From a start point to an end point. So for us, that's going to be from 0 until we said 9 earlier. Of RHW. So this 2 pi is from our circumference. We've already pulled it outside the integral. Our r is our distance to the axis of rotation. This is the hard part. So my radius is my distance from colors. Here we go. My radius is my distance from here at the axis of rotation to here, our x value right now. Okay, so if our distance from where we are right now to 0 is x, and our distance from 0 to -1 is 1, then what's the total distance from where we are to -1?
It's -1, so that's like 5. So like 4. No, wait, or 8. For the radius would be.
Okay, let me go back a little bit. So, this distance from here to here is going to be whatever x is right now. And this distance from here until here is 1, since we're spinning around the axis -1. Okay, so if all of that is true, then what's the total distance here in purple?
Five. 4.
Okay, not 4. This value is going to change based on where our box is in the shape. So it could be from 0 all the way up to 9. So it's going to have a variable in this equation. Okay, the distance here in light blue is x. The distance here in yellow is 1.
1 plus x.
1 plus x. Okay, is our radius. Okay, so I've got 2 pi times our radius. I'm just going to write r for now. Radius times height times our width, which is dx. Okay, any questions on what happened here?
No.
I'm going to type this out as maybe shell method, and we'll post this out for notes. Okay, I'm 2 minutes past due, so we'll finish typing this one out and then we'll stop here, I think. So moving this back into our shots. Our volume of the solid when we spin about that vertical line then is going to be equal to, if I plug everything in, the integral from x equals 0 to x equals 9 of 2 pi, which I'm going to pull outside the integral, of our radius, which we said is 1 plus x, times our height, which we said was the square root of x, minus x over 3, times our width, which is dx. Okay, we will type that into a calculator and get an answer for it. So this is 2 times pi times the integral of our radius, 1 plus x, times our height minus our width. Root x minus x over 3. In terms of x from 0 to 9. Or 130.06 for our volume. Alright, any questions on anything from A or B that we've done so far?
No.
Okay, I'm going to stop there for now. Let me get a year for this really quick before I forget so we can find it for next time. This is 2008 Form B. I'll post that to the chat as well, so if you want to see the last part of that, we can start next class period with that if you remind me.
Okay.
Alright, thank you very much for coming. Sorry to keep you over. And if you come tomorrow, I'll see you then, okay?
Bye.
Goodbye.